We want to prove a theorem on the product of step discontinuous and Dirac delta functions, which are both distributions, also known as generalized functions. Let U be the Heaviside unitary step function and delta its derivative, which is a Dirac delta function. Let f be a smooth function defined over R. Now, the theorem would work also with f local integrable, but for the purpose of this video we will assume f smooth. Note that f of u is once again a step discontinuous function. The theorem states that the product of f of u times delta is a Dirac delta function, which amplitude is the integral from 0 to 1 of the function f. Although a formal proof of the theorem would be not too difficult, in this video I will give an informal proof. Let g be any smooth function which goes over R from 0 to 1. We define the sequence of function Sn to be g of nx. Clearly the limited for n that goes to infinity of Sn is the Heaviside function. Deriving both sides of this limit, we find a sequence of function Sn prime, which limit is the Dirac delta function. Finally, we define the sequence f of Sn times Sn prime, which limit, if it exists, is the product of distribution we are looking for. I want to show visually what's going on here. If we choose any random f and g functions, then for n that goes to infinity the sequence f of Sn goes to a discontinuous step function. The sequence Sn prime goes to the Dirac delta function. Now, the product of the two sequences goes to 0 for all x not equal to 0. This is because, for all x not equal to 0, it is the product of a sequence that becomes flat, times a sequence that goes to 0. We want to evaluate this integral. This integral is not difficult to evaluate. This is because the integrand is simply the derivative of a composite function. We use the definition of Sn. And we get the final result. The integral is constant and independent both from n and from g. It depends only on f. We conclude that this sequence goes to a Dirac delta function. Our product of distribution is well defined. It is a Dirac delta function and it is the limit of this sequence. This proves the theorem. However, when I use the equal symbol in this expression, I am cheating a bit. If the two sides of the expression are elements of a Colombo algebra, then they are two separate elements that can be associated by means of the association relation. They differ by a null function in the Colombo algebra which is equivalent to a zero constant function in the Schwarz theory of distributions. To be correct, we should state the theorem using a different symbol to show that this is an equivalence rather than an equality. There are two ways we can generalize this theorem. First, the step discontinuous function does not need to jump by one only. Let s of x be a step discontinuous function that jumps between any two values in 0 and delta, its derivatives, apart from a multiplicative factor to normalize the delta to an amplitude of 1. If f is an integrable function over R, then we have that f of s times delta is equal to a delta function which amplitude is given by this expression. Second, we can generalize to multivariable functions. Let s1 of x and s2 of y be two step discontinuous functions that jump between any two values in 0. Let delta 1 and delta 2, theirs derivatives, apart from a multiplicative factor to normalize the two deltas to an amplitude of 1. If f of x and y is an integrable function over the xy plane, then we have that f of s1 s2 times delta is equal to a delta function which amplitude is given by this expression, where delta of x and y is the product of delta 1 of x times delta 2 of y.